All right, so yesterday we talked about experimental or estimated probability, where you just sort of use data from performing a chance experiment over and over again to figure out an estimate of the probability of something occurring. But as we know from our real life experiences, those numbers aren't always correct because, like when we flip a coin, we have a general understanding that it should have about a 50-50 chance of landing on heads or tails. But we could run a chance experiment of flipping a coin 5 times and get 5 tails in a row. And then based on that data, we would have to conclude that there's a 100% chance of landing on tails, which we know is not true, right? Um, and so with theoretical probability, we're calculating what should happen, right? Experimental probability is all about like what did happen. Theoretical probability is all about what should happen. And so let's start by just looking at the formula for this. Um, let's not worry about this one too much. This is like a simplified version of it. We don't need to worry about this. This is the general one that is more important in my opinion. So the probability of some event happening, some outcome, whatever, the thing that we're looking for to have happen is the number of favorable or desired outcomes divided by the total number of possible outcomes. And this number of possible outcomes, all those outcomes combined have a really kind of weird name, but it's super important that you understand this name and that like when I say it, you know what I'm talking about. This is called the sample space. This is super important vocab term here. So I want you to try to really understand what I'm saying here. Is that when you list out all of the different ways a chance experiment could go, right? You actually write out, if I were to flip 2 coins, I could get heads, heads. I could get heads, tails. I could get tails, heads, and I could get tails, tails. Those 4 outcomes and listing them out properly like that, that is called the sample space. And being able to list the sample space for a chance experiment is key to being able to calculate its theoretical probability. If you can't list out the entire sample space accurately, then you can't calculate theoretical probability for a chance experiment. All right, so another way people say this formula is it's the number of ways to get your desired or favorable outcome divided by number of outcomes in the sample space. All right, you're probably still confused about this whole sample space idea. So let's do it a few times and then hopefully that becomes more clear, right? All right, so let's start with example 2. It says, an experiment consisted of flipping a nickel and a dime. All right, so you got a nickel in one hand and a dime in the other, and you flip the nickel and you flip the dime and see what you get. The first step in finding the theoretical probability of obtaining a head on the nickel and a head on the dime, okay, so that's our desired outcome in this question. It's basically heads, heads. They want heads on both coins, is to list the sample space. For this experiment, the sample space is shown below. So these are all the possible outcomes that could happen when you flip these 2 coins. You could get heads and heads. You could get heads and tails. You could get tails and then heads. And those are different, right? Because in this one, the heads came up on the first coin. And in this one, tails came up on the first coin. And on this one, tails came up on the first coin, and on this one heads came up. So like even though it's a heads and a tails, they're unique outcomes. They're still considered different. And then the 4th possible outcome is that both coins come up tails. And these are the only 4 possible outcomes that could possibly happen when flipping 2 coins to see whether you get heads or tails on both of them. And so these 4 outcomes combined and listing them out in this way, that's called the sample space. And so now we know that there are 4 possible unique outcomes to this chance experiment. And so each outcome has a 1/4 probability of happening because it's 1 out of 4 possible ways that the experiment could go. Okay, so here it says the probability of 2 heads is 1/4, or in other words, P of 2 heads, probability of 2 heads equals 1/4. So they're talking about this one outcome right here. This one outcome has a 1/4 probability because it's 1 out of these 4 outcomes, and they're all equally likely. That's an important part of this. Like, yeah, it's 1 of 4 possible outcomes, but each of these outcomes has the same like probability or same chance of happening. You can have experiments where there's only like 2 outcomes, but one has a way higher probability of happening. Like if I were to flip this marker, and let's say there's only 2 outcomes, either an outcome where it lands vertically like this, which I can't even really do when I want to, or an outcome of it landing horizontally like that. Okay, there's 2 outcomes. So that doesn't mean that this outcome has a 1 out of 2 or 50% chance of happening, because we all know that it's super rare to be able to flip a marker like that and get it to land vertically. I could probably try literally 1 billion times and not get it. So this idea of listing out a sample space and then dividing the number of desired outcomes by the number of total outcomes or possible outcomes only works if all of the outcomes are equally likely. You can't have some weird experiment where, of course, one thing has a better chance than the rest. All right, so consider a chance experiment of rolling a number cube. For some reason, this book doesn't like to use the word die. They're talking about a die, but they call it a number cube. What is the sample space? Okay, so there's 6 possible outcomes when you roll a die. You could, anytime you list a sample space, you can make a nice little like column organized thing here like they did here and here. You can put them into a table if you like. I like to just do the simple thing, which is just list them out with commas between. So a possible outcome would be you roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, and you could roll a 6. So there's my sample space for this chance experiment, listing out the 6 possible outcomes. And list the probability of each outcome in the sample space. Well, okay, this is kind of a lot of work, but the probability of 1, rolling a 1, equals 1/6, because it's 1 out of 6 possible outcomes and they're all equally likely. And the probability of rolling a 2 equals 1/6. And the probability of rolling a 3 equals 1/6. And the probability of rolling a 4 equals 1/6. And the probability of rolling a 5 equals 1/6. And the probability of rolling a 6 equals 1/6. And if you added up all these probabilities, 1/6, 2/6, 3/6, 4/6, 5/6, 6/6, they add up to 1 because they're the entire sample space. They're all the possible outcomes. So when you add up their probabilities, it has to add up to 1 every single time, or else you messed up, because you should have a probability of 1, or in other words, 100% chance of getting one of these outcomes, right? So the probabilities of the entire sample space should make 100% every time. What is the probability of rolling an odd number? Well, so in order to answer this, I need to look at the number of ways to get an odd divided by total number of outcomes in the sample space. In the sample space. Okay, and so the total number of outcomes in the sample space is 6, right? 1, 2, 3, 4, 5, 6. Okay, so it's going to be a 6 on the bottom. And then the number of ways to get an odd. Well, you can roll a 1, a 3, or a 5. Those are your 3 odd outcome possibilities. So it's 3 out of 6. And that simplifies down to a half or 0.5, right? So in other words, you got a 50-50 chance or a 0.5 of rolling odd, right? And the other 0.5 probability is rolling an even. Okay, now what is the probability of rolling a number less than 5? Okay, so the probability of like rolling a number that is less than 5. Okay, so that's how I would write that. And that's going to be the number of ways to get less than 5 divided by number of outcomes in the sample space. I'm kind of shortening my writing now. Okay, and so the number of outcomes in the sample space is still 6. There's 6 possible outcomes to this chance experiment. And how many different ways are there to get a number less than 5? 1, 2, 3, 4. I don't count 5 itself because 5 is less than 5. So there's 4 out of 6 ways. That's equal to 2/3, which is equal to 0.6 repeating. So you got a 0.6 repeating probability of getting less than 5. Yeah. All right, let's move on. Consider an experiment of randomly selecting a letter from the word number. Okay, what is the sample space? Well, the sample space is just each letter, right? If you're randomly selecting a letter from the word number, you could get an N, you could get a U, you could get an M, you could get a B, you could get an E, and you could get an R. There's my sample space. And the probability of each outcome in the sample space, well, they're equally likely, and there's no repeaters, right? Like there's not like 2 N's or 2 R's or whatever. So each one, I'm going to be lazy here and just write P equals 1/6, because there's 1, 2, 3, 4, 5, 6 for each, right? Rather than like writing them all independently. Okay, and so what is the probability of selecting a vowel? So I'll write the probability of getting a vowel equals, it'll be the number of vowels, 1, 2, divided by the total number of possible outcomes, which is the 6 letters. So 2, 6, which equals 1/3 or 0.3 repeating. Okay, and what is the probability of selecting Z? Well, the probability of getting a Z equals 0 because there are no Z's. Okay, so that one's just like a stupid trick question. All right, I'm gonna skip a couple of these. I like this one better because this one is what we would call a 2-stage experiment, where like you're doing one thing, right? The first stage is to spin this spinner that has red and blue, and then the second stage would be to spin this spinner that has red, blue, green, yellow. And yeah, I just think these are a little bit more complex and they're worth talking about. So students are playing a game that requires spinning the 2 spinners shown below. A student wins the game if both spins land on red. So you want to get red here and red here. What is the probability of winning a game? So first let's out the sample space and then look at the outcomes in the sample space. So the way we answer this question is let's look at all the different possible ways this chance experiment could possibly go. And then let's look at how many different ways there are to win, which I think in this case is just landing on red, red. And then we can use that information to calculate the theoretical probability of winning this game. So sample space. We do this methodically, right? We go through them in an order that makes sense for us so that we don't accidentally like skip one or mess up. So I'm going to start with, let's pretend in stage 1, I landed on red. Then in stage 2, I'm going to go through all the different possibilities that could happen after landing on red in the first stage. So I could get red and then green. And so I'm going to write that as RG. Then I could get red, yellow. So I'm going to write that as red, yellow. Then I could get red, blue. So I'll write that as RB. And then I could get red, red, which is our desired outcome. So red, red. Okay, so now I've exhausted all the different possibilities that could happen after you get a red in stage 1. So let me move on to stage 2. You could get a blue, and then it's going to be the same combinations as here, right? I could go blue, green, blue, yellow, blue, 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 red. So blue, green, blue, yellow, blue, 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 red. So there are 8 outcomes in the sample space. So that's an important number for us, right? Okay, and then this is the one we want right here, right? You win this game if you land on red in stage 1 and red in stage 2. And there's only one way to win. One desired outcome. So the probability here is our one desired outcome divided by the 8 outcomes in the sample space. So the probability of red, or winning in this case, equals 1/8, which I know is equal to 0.125 as a decimal. So you got a 1 out of 8 chance of winning that game. By the way, there were 2 possibilities in stage 1 and 4 possibilities in stage 2, and 2 times 4 equals 8. Or in other words, we had like 2 rows here, one where they all started with red and one where they all started with blue, and each row had 4 different outcomes in it, and that got us our 8, and that pretty much always works. So you can kind of always tell how many outcomes like a multi-stage chance experiment's going to have by just multiplying the number of unique outcomes in each stage. All right, so let's move into the problem set a little bit here, because there's some good questions in here, and I just want to talk about them in here. Yeah, so I want to just do number 5 real quick. It says a chance experiment consists of flipping a coin, okay, so heads or tails, and then rolling a number cube, right? They're talking about a die, with the numbers 1 through 6 on the faces. List the sample space of this experiment. Okay, so I'm working down here. Sample space. This is a two-stage experiment. Flipping the coin is stage 1, and rolling the die is stage 2. When you flip a coin, there's 2 possible outcomes, heads or tails. So there's 2. And when you roll a die, there's 6 possible outcomes, 1 through 6. And so that means that in my sample space, there's going to be 12 possible outcomes, because I'm going to do 2 times 6. I'm going to list them out anyway, so even though I know it's going to be 12. So the first thing I could get is heads on the coin, right? And so I'm going to stick with heads, but I'm going to list all the different things that could happen when I get a heads. I could get heads on the coin and then 1 on the die. Heads on the coin, 2 on the die. Heads on the coin, 3 on the die. Heads on the coin, 4 on the die. Notice I'm only putting the commas between the outcomes. I'm not putting a comma between H and 2. That would be too confusing. So heads and then 5, and heads and then 6. And now I just do the exact same thing, but just imagining that I got a tails in stage 1. So tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. And so we got our 12 possible outcomes in the sample space here. The reason it's important to still list out a sample space like this, even though we know that there's going to be 12, is because listing it out like this allows us to answer really complex questions about, like, well, what is the probability of getting like a heads and then a number less than 4? And then you can literally just go count the ones that meet the criteria of the question. And that's probably exactly what it's going to ask us to do here. So let's go to B. It says, what is the probability of getting a head on the coin and the number 3 on the cube? Okay, so you have to get a heads and a 3. That's a very specific thing, right? The only one that does that is this outcome right here, heads and 3. And so for B, the probability of heads and a 3, well, that's just one favorable outcome out of the 12 possible outcomes, so it's 1/12. I don't know off the top of my head what a 12th is. I want to say it's like 0.085 or whatever, but we'll just leave our answer as a fraction this time. That's fine. Okay, and then C says, what is the probability of getting a tail on the coin and an even number on the cube? Okay, so this one's going to have multiple ways to win, right? Multiple favorable or desired outcome. As long as it has a tail and an even number. So I'll just like circle those in pink, the ones that count for this. Oh wait, it says tail and even, and I circled an odd one. Not correct. Oops. Let me use a different color now. Use black. Okay, so I want tails and 2. I want tails and 4. And I want tails and 6. So I've got 3 desirable outcomes that meet the criteria for question C. And it's out of the 12 possible outcomes. So the probability of tails and even, I guess I'll write that as tail colon even is how I'll write that, equals 3 possible ways to get that divided by 12 possible outcomes in the sample space. And so that's the same as 1/4 or 0.25. And see how like we can, by listing out the sample space and then just counting the desirable outcomes, we can answer some pretty complex questions, right? If somebody just came up to you before I showed you how to do this and said, okay, flip a coin and roll a die with 1 through 6 on it, what's the probability that you get a tails and an even? You'd be like, what? Like, how am I supposed to even know that? Like, that sounds super complex. But when you just list out all the like ways that the chance experiment can go, and then just count the ways you get what you want, it turns what is a really, really complicated question into something that's just like counting and then building a fraction out of it, right? So, all right, that's that.